In this lecture on dry etch, we are going to look at plasma characteristics. So, in the earlier lecture, we discussed about the nature of the plasma, right? What are all the constituents of plasma and how we generate plasma and how to sustain the plasma. In this lecture, we are going to look at the configuration that we normally use, right? How do we supply energy to the plasma, right? And then also look at how we use this plasma for etching, right? Why we actually are interested in using plasma process as opposed to wet chemical process to define patterns. So, let us look at why we need plasma etching. First of all, plasma etching could be done or can be made anisotropic, right? What is anisotropic? Isotropic, we know it's equal etch in all the direction, right? So, both horizontal and then the vertical etch is going to have the same rate, right? The etch rate in vertical will be equal to etch rate in horizontal direction. So, if you take a material that is covered with photoresist and then if you expose it to any wet chemical, which normally does any general wet chemical, you will get a profile like this. The reason for that is the vertical etch rate is equal to the horizontal etch rate. So, you will not be able to get very smooth or very sharp sidewalls. Right. So, in order to achieve sharp sidewalls, you need what is called anisotropic, that is directional etch. Right. So, where your vertical etch will be much larger than your horizontal etch rate. So, this is what you would like to achieve, and this is achievable in a plasma etch process, right? And the next thing is the consumption of chemicals can be controlled. Because you are using a chamber, we can control the chemical consumption, and that will directly result in cost reduction, and also a controlled disposal of all these chemicals could be done. So, some of the chemicals are toxic, so we do not have to expose it to human beings, right. So, we will contain it in the chamber so that we can dispose it clearly, and it is a clean process because it happens inside the vacuum. So, we can be assured about the contamination that you get, and we can also automate the whole process, right. So, we can employ this in manufacturing as well. And the other thing, as I mentioned, when you can make anisotropic pattern, the pattern can have a very precise transfer as well. So, this is what the isotropic and anisotropic as we explained in the last slide, right. So, you have a mask and you have silicon in this case, and we want to etch the material, right. In isotropic, you will see etch in the lateral direction as well. Okay. So, this is the result of equal etch in vertical and horizontal direction. But then if you look at anisotropic, that is directional, you normally refer to this sort of pattern where you do not have any lateral edge, you have edge only in the vertical direction. However, if you choose some of this chemical, for instance KOH, right, potassium hydroxide, actually this one this chemical etches silicon in a directional way. That means based on the crystal orientation, you will see there is a directional edge. In this case, we cannot call this as isotropic, it is still anisotropic, right. It is directional edge. In some crystal planes the etch rate is higher, and some you will have very low etch rate. So, that is also directional, right. So, when you talk about anisotropic, we have to be very clear about the process. Is it directional or is it vertical edge, right. So, directional need not be vertical only, right. So, when you are talking about this anisotropic edge, you should also consider whether it is directional or whether it is vertical distance that you are talking about. The other thing is isotropic nature or direction. How do we actually find out if it is isotropic or directional. The only way to do that is when you are doing the process development, you should keep the photoresist here. So this is your photoresist, and then you have done the process, right? And then when you are doing the process, don't remove the photoresist, keep the photoresist, and then look at the cross section, right? So you can make a pattern, right, and then you cut this pattern, right, and cut the pattern and then look at the cross section. And when you look at the cross section, you will know that there is an undercut here. If you remove the photoresist, you will end up with a pattern like this. For instance, if you have overetched, and in this case you don't know whether this is isotropic or whether you have done a directional etch, right, which we saw in the earlier slide, that directional also is anisotropic, right. So you need to be careful about this. So when you are doing process development, keep the mask, right, always keep the mask, so that you know whether it is a directional etch or isotropic. So any kind of misinterpretation could of course lead to wrong conclusion. So when you are doing process development, make sure that you extract maximum information from the experiments that you do. So when you keep the photoresist here, you will know that it is not directional etch, it is a undercut. And the next thing is about directionality again on a topography wafer. So what is a topography? Is nothing but a surface with corrugation, which is a non-planar, right? When you have features and when it is etched and so on, we call that as a topography. So now you have a topography, right, and then I filled with some material. Let's say this is silicon nitride, right. So I fill this material, and then if I take this material for dry etching, right. So we go for dry etch, right. And there are two things that can happen. One is highly directional etch, one is isotropic etch. If I do isotropic etch on this filled wafer, I will remove all the nitride that is present in both vertical and lateral, because I am doing isotropic etch. So I will remove the material here, right. I will not find any nitride at all. But then if it is highly directional, that means I am etching only in one direction, right. If that is the case, then my lateral etch is almost 0, right, in this case, ideal case. So I will see this side walls, right. So I can fill or coat these side walls by using a highly directional edge, and this is the process used in spacer definition, right. In optical lithography, for multiple patterning, we had this spacer defined multi-layer patterning, right. So we use this kind of directional edge to define these spacers. Okay. So the reason for that is it's a uniform thickness, right. So when the etch is happening, right, let's all over the place, and this is the thickness I have here, but in this case it is T plus capital T, let's say, right. So while I remove this thickness here, the remaining thickness is left, right, on the side wall. So this is how you end up with a side wall coated film. And these are all the methods that we use, right. So dry etch can be done using various methods, and broadly classified under glow discharge method and ion beam methods, right. In glow discharge, you can use plasma etching, right, which is low energy, right. LE means low energy, and it can be reactive ion etching, and then it can be glow discharge sputtering, right, which is also high energy. So in case of plasma etching and reactive ion etching, we are going to use reactive gases, right, in both the cases. But if you look at sputtering, you use inert gas, right. So similar to PVD, right, a physical vapor deposition that uses sputtering process, here again we use an inert gas and then accelerate those molecules onto the substrate to sputter the material away. There is no chemical reaction, but in the above two cases you have some chemical reaction to convert solid to gas. And the next method is ion beam, right. So here instead of having a discharge, we are using ion beams, right. So you make a inert gas ion beam, right, and you focus that ion beam and then direct it towards the substrate. So when you do that, you also get material removal. So here again no reactive neutrals, right? So there is no reaction happening. It is going to be again a physical process. It's going to kick out the material by pure force, right? So there is no chemical reaction involved. The other thing is chemically assisted ion beam etching. So here, in addition to the ion beam, we are going to add some reactive neutrals. So that means you have both ions and also some reactive species. So later on we will see how these processes are really fundamental, but in this case both physical and also chemical etch happens, right? So physical etch meaning only force is used to remove the material, chemical etch meaning you create chemical reaction and those products are made volatile. And reactive ion beam etching, right? So reactive ion we know, so we create these reactive ions and then direct those beams, right? So that is again another way of doing etch. Instead of creating inert gas ions, here the ions are reactive, they can react, and then you also create reactive neutrals add to this to do the etching. Okay, these are all the broad classification of dry etching methods. And then if we look at the etching parameters, the plasma parameters, there are huge lists, right? So this is a selection of that list. So on the right side you see a very simple parallel plate reactor. So why we call this as a parallel plate? It looks like a capacitor. You can see here two electrodes, and in between you have a gap, and within this gap you create the plasma, right? And then you will see this dark space on the top electrode and the bottom electrode, which we will see shortly why those things are coming in. But then there are two type of plasma parameters. One is the excitation frequency. We are going to feed some energy, right? So that energy frequency, right, it can be DC also, and it can be RF. So what is that, right? And then the power that we give, right? How much power we are going to give. And then the gas flow rates, because the plasma can be only generated when you have sufficient number of molecules in, right? So what kind of gases we are putting in, and what is the flow rate. The nature of the discharge itself, right? With the chemical and the electronic property of this gas is also important. The geometrical factor, right? The size of the electrodes, right? Between the power electrode and also the ground electrode, and the wall that we have, all those things really matter. And then the pumping speed, right? The pumping speed also determines your pressure and so on. You can also say the gas flow and pumping speed together contribute to the pressure inside that. So that is again an important parameter. So this is the bulk plasma properties, right? How do we control that? So next, plasma to surface, right? So plasma surface interactions are very important, because we are going to keep our wafer somewhere here, right? So when you keep the wafer here, it's not bulk interaction. The plasma should interact with the surface, right? So that depends on nature of the surface. If the surface is conducting, or whether the surface is insulating, and then the surface geometry itself, right? Whether it is very small piece, very large wafer, so all those things matter. Temperature, right? What is the surface temperature? Because surface reactions are affected by the temperature as well, right? So whether the temperature is kept constant, or it is done at lower temperature or higher temperature, so that affects the reaction on the surface. The last thing is about the potential. Because we generate all the interesting radicals in the plasma, so you have ions, neutrals and electrons there. So when you have a surface, what is the potential of the surface? So based on the potential of the surface, you can either attract or repel the species, right? So based on the surface potential, your plasma surface interaction will be affected. So let's look at some of these discharges, right? Both on the bulk side and also on the surface side. So it will create a lot of electrons, of course. In this case, we are taking a simple CH4 methane plasma. So you will generate positive ions, you will generate atoms and radicals, right? So you have a huge combination, right? CHX is a combo, so you can have various composition one can get, right? So you are dissociating the precursor gas. The next thing is you can have electronegative ions, you can have neutral molecules, and also excited states as well. So as the molecule becomes complex, you will also get all possible constituents in the plasma, right? So which makes the plasma very rich, at the same time very complex to study as well. So let's look at another type of gas. Here we are taking oxygen. Very simple, right? So in the previous part it was CH4, in this case just O2, right? So here already you can see the combinations are limited, right? So this also gives you a better understanding of how you can study the discharge, right? And also in terms of controlling the chemistry, if the material, the molecule is very complex, it will have multiple dissociation components, which will be very hard to actually control and so on. But in this case, if you are working with oxygen, it's pretty straightforward. And the next thing is argon. Argon is very simple because it's an inert gas, right? So what you do is you only create positive ions and electrons, or neutral argon atoms as well. So that is the only possible constituents that you can generate using argon. So the idea here is when the gas is very simple, it's easy to understand their plasma phases, but then when the gas becomes more complex, then the chemistry also becomes very interesting. And in some of the cases, you want to make this chemistry a little bit complex, so that you have handle on which paths to control, and you will have a possibility of controlling different type of species. And this is the relative density of different species, right, that you have in both low density discharge and high density discharge. So you will have H gases, right, and then we'll have H products, radicals, and then the charged particles. So you can clearly see the charged particles, right? The amount of charged particles in a low density plasma is pretty low, right, while when you get the radicals, they are pretty high. However, in a high density plasma, all the compositions are pretty high, right? So your H gases, radicals, H products, and also charged particles, all these constituents number counts are high, right? So if you look at both the cases, low density or high density, you will naturally gravitate towards high density, because you have efficient conversion of your H gases to radicals and charged particles, right? So that is what you want. But in a low density plasma, your charged particle numbers are small, because charged particles again also include electrons, right? So that becomes very essential to create dissociation and then also participate in plasma sustenance. Okay, so high density and low density, based on the requirement of the process, one can choose, and this should give you an idea, what is the number count of these various particles. And in plasma, as I mentioned earlier, even in the last lecture, electrons are the most important particles, right? So electron mobility inside the plasma is one of the important activity that keeps or sustains the plasma. So electrons that are mobile in the plasma, right, much more than the ions. The reason for this is very simple. It's the mass, right? So electrons very low mass, so they can easily respond to the potential difference, right? And because of this mobility of both electrons and positive ions in the plasma, you will have various potentials developed. So let us look at these things one by one. We call floating potential, plasma potential, and self bias voltage. So these are all the potential that is developed because of this nature of electron and ion mobility. So first thing is plasma potential. So what is plasma potential? So the plasma potential is measured by using an insulating surface, right? So this is a highly insulating surface, and then we insert this insulating surface inside the plasma. Okay, so let's assume I have created a plasma in this zone, right? So this is connected to some source, and then this is grounded, and this is going to be our plasma. So what is the floating potential? Floating potential is nothing but I put a glass here, let's say. So I take an insulating layer here. So if I take this insulating layer and insert it into the plasma, and now I am monitoring what is the current that is developed in this sheet, right? So what will happen when I insert? The first thing that will happen is a large number of electrons are going to come and hit the surface, right? So when this large number of electrons are going to hit the surface, you will create a negatively charged layer, because it is not grounded. It is very important to note this the insertion that we do is not grounded, right? So all the electrons will be accumulated and you will have a negative charge, and once you generate this negative charge in this insulator, you are going to attract positive ions, right? So now you are going to start to see ion current. Initially you only had electron current, right? So you slowly develop the electron current there, but then once you reach a certain voltage, the negative voltage, you are starting to attract ions, right? So now ions are coming in. So now these ions are also going to contribute or neutralize this and contribute to the potential there. So at some point both these electron current and ion current will sort of neutralize each other, and that is what we call floating potential. Okay, and the next is a plasma potential, right? This is similar to what we saw earlier, but the only difference is we are going to ground, right? So what is the potential, right, inside the plasma when you ground it, right? So this is what we are interested in. So when there is a grounded chamber, right? So inside a grounded chamber we are trying to look at, and the same thing would happen here as well, right? So once you insert it, so you will have electrons coming in, and then you will also see after a certain accumulation of electrons, you will also see ion current, right? So both of these currents will neutralize each other, trying to arrive at a certain potential, which is called the plasma potential. And the other thing, important thing here is the direction of your, or the polarity of your voltage here, right? So here you see this is positive, right? While the floating potential that we saw, that is negative, right? The reason for that is the electron current, right? So you start with very large electron current, and in this case it is grounded as well, right? So that is the reason why your plasma potential will be always be slightly positive, right? And the other thing to note here is the electrons that are inside this plasma would always scatter and then can reach the wall, right? And this wall will also ground it, right? So you can, this is called electron loss from the plasma, right? And this electron loss will make this plasma slightly positive. If you remember, plasmas are neutral, right? In principle plasma should be neutral, but because you have a grounded cover here, you will have some electron loss, right? And this electron loss will make the plasma slightly positive. Why only electron loss? Why not ion loss? The reason for that is the mobility of electrons, right? The electrons are much faster, and also they scatter a lot. The scattering is the one that makes this electron go and annihilate itself in the chamber walls. Okay, and this is all about plasma potential, right? So there are two ways to look at it. Either you put the layer inside, or whatever you measure from the chamber wall itself, right? The potential between the plasma and also chamber wall is also your plasma potential, because the chamber walls are also grounded. So let's look at whether the energy that we give to the system, the nature of that energy that we give has an effect on the plasma or not, right? So let's look at two cases. One is DC glow discharge, the other one is RF. Let's first look at DC discharge, right? So we take a parallel plate, right? It's a capacitive reactor. We take a parallel plate, and then I'm giving a DC. It's a DC source, VC, right? And one plate is energized. This is called the cathode plate, and then this is the anode plate, which is grounded, right? So when you apply a negative voltage to the cathode, right? So in this plate, you are going to attract some positive ions, right? So initially you will not have anything, okay, to start with. So this is when you are switching on your the system, right? So you will not have anything, but you will have some charged particles anyway, right? And these charged particles will be accelerated. Let's assume this is a positive charge. This will be attracted to the surface, right, with a certain acceleration, because you are applying a voltage here, right? When it hits the surface, you expect some electrons to come out, right? So this is the ejection of electrons. When the electrons come out, it will be repelled by the cathode and accelerate towards anode, right? And during its motion towards anode, it is going to encounter other molecules, and it will collide with those molecules, okay? So and this collision is what creates dissociation, ionization, and also additional electrons, right? So in order to make this happen, you need both electrodes to be conducting, right? That is again an important property. So let's look at the energy of these ions and electrons. So a positive ion, right, that is accelerated towards the cathode will have the energy equivalent to E times Vp plus Vc. Vp is nothing but plasma potential, okay, and Vc is the drive potential that we apply, okay. So this is the accelerating voltage you can apply, and you can vary this based on your applied voltage, right? And then if you look at the voltage or potential across the two plates, you will have negative potential that we apply, right? So that is what we apply as a DC. But as you move inside the plasma, it will become slightly positive, right? So this is the positive side and this is the negative side, right? So your plasma potential is slightly positive. So we already saw the plasma potential is slightly positive because of the electron loss that you have, right? The electrons are going to scatter a lot unlike ions, and you will have electron loss, creating slightly positive potential. But then once it reaches the other plate, it will go to 0, right? And you can see here there are 0 crossings, right? So you see the 0 crossings here and here, which are interesting points, right? Later on we will see how this affects the way the glow discharge actually looks, right? And next is the RF glow, right? Instead of DC, we replace it with RF source. But you have to note it's not just RF, but we put a blocking capacitor, right? So this is a blocking capacitor. So this blocking capacitor is between the power electrode and RF, and the other electrode of course is grounded, okay? So now we call this as a power electrode, and this is ground electrode, okay. So now when I pump RF power through this blocking capacitor, I can push energy into it, and then in the same explanation holds true here as well. But one interesting thing that you should note is the potential here, right? Initially we had VC, right? So whatever supply voltage we had, that was the potential you had on the in a power plate, right? But now it is VDC, it's not VRF, right? So if this is VRF, right, it's not going to be VRF, it's going to be VDC. So this VDC is nothing but your capacitor, right, whatever the capacitor could hold, right? So the VDC is nothing but the self bias voltage, right, how much charge the blocking capacitor can hold, and that becomes the VDC. Okay, and then the plasma potential that we get in RF glow discharge is much larger than DC. The reason for this is efficient power transfer, right? So we'll see why it is efficient in the next slide, but the plasma potential is very high, which is important so that your plasma is very energetic, right? And again, the ion energy, right, to reach the power electrode depends on your plasma potential, and now it is VDC, right, instead of VC. So in DC glow discharge it was VC. So that is your DC power that you supply here. In this case, the ion energy reaching the power electrode depends on your self bias voltage, right? And the ion energy reaching the wall, right, on the other side. So the ions can also reach the other side, and that energy only depends on the plasma potential alone. Okay. So the ion bombardment or the plasma sustenance is primarily handled with electrons, as I mentioned. So electrons will reach the electrodes and also the chamber walls, right? It's not just the electrodes. What I mean by chamber wall is we are just looking at two electrodes, right? But it will be enclosed in a chamber, and that chamber will also be grounded, right? So the electrons can also scatter and reach there as well, right? So electrons will be repelled from let's say in this case from the cathode, right? And that would generate some sort of repulsion here, and then the ions are going to be attracted there, right? And normally the ions are accelerated through this potential drop, right, towards the electrode, and the reason for that is the accumulation of charges there in this positive potential, and then you're going down to zero, right? And this part you can see this in the image as well. So here what you see is a grounded electrode, and then this electrode is connected to your a DC supply, very large DC supply. You can see a bright line here, right? And then you will see a dark spot. So there is a dark region here, right? And then from here on it becomes bright. So this is where your transition happens, right? The potential transition where you have lot of collision and so on. So this color is from excitation, right? We saw in the first lecture that the generation of emission, right, is from excitation process, and that is the excitation is pretty large. That means that you have larger collision very close to the substrate, and also in the plasma as well. Between these they are very minimal collision because of reduction in the acceleration. Let's look at the RF feed again, but now we are going to look at the time dependency of this voltage, right? So when you take a RF, right, so this is the RF feed that you have, and also let's look at the potential across the two electrodes, right? So let's say this is the ground electrode, and here I am feeding an RF with a blocking capacitor, of course, right? And here we are going to swing between positive, negative, and then zero, right? It is going to go through zero as well. So when RF is positive, right, so this is positive, your plasma potential and your electrode potential are identical. So in this case the electrons will be attracted to the surface, and they will be accumulated on the surface. So now when I am going to go to the negative cycle, it is a complete change of polarity. Now it becomes a negative, and it will be repelled. All the electrons here are going to be repelled, and this repulsion is the one that gives acceleration and the energy to the electrons to go into the plasma and then create collision. But then the solid curve here, the black solid curve here, shows the time average that we see here, right? But in reality, you will swing between positive and negative, and what you see here is the DC bias or self bias that you see here coming from the blocking capacitor, and then you see how the potential is stabilized inside the plasma. And that brings us to end of understanding the plasma characteristics, and in the next session we will look at what are all the tools that we can use to exploit the plasma here for various purposes.